In this presentation, we're going to learn about alkynes and we'll focus on their nomenclature, properties, and synthesis. So let's look at simple stuff about alkynes. So first of all, alkynes have a triple bond in them. So a triple bond means that they're sp hybridized, which is a 180 bond angle, and then linear in shape. Alkynes also have 2 degrees of unsaturation, which means that they have 4 hydrogen less than the corresponding alkane. All right, so those are some of the basic stuff about alkynes. Then alkynes, so alk and then ines. Okay, so regarding the nomenclature, it's kind of very straightforward. You can start with the first one, which is ethyne. There is no one carbon alkyne, right? You can write the formula and see you'll be lacking hydrogens seriously. So the first alkyne is ethyne. Ethyne is the only one that also has a common name, acetylene, and you might have heard of it as acetylene torches, like the mechanics and welders use because it's very high heat. But anyhow, okay. So the way we're going to do the nomenclature is, of course, the alk part, which is the number of carbons, and then ine, which is the functional group, right? So ethyne, propyne, and then butyne. Once we get to butyne, we have to number, and yeah, I can already see that this one should be 2 here, so we'll change that. So you have to tell the location of the triple bond, so whether the triple bond is on the first or second, so location, that's important. The interesting thing about alkynes is that you will come across a carbon that has no hydrogens, okay, especially the internal carbons. And so here the 3 bonds are to the carbon and the other 4th bond is to the other carbon, so there is no place for hydrogen. Okay. The other thing I want to mention over here, and I will move on in a second, is how to write out the alkynes. When you write alkynes, I would like you to start from drawing the triple bond. Okay. When you're writing a condensed structure, this is fine. All right. But when you're drawing the line structure, you should not be doing this for the line structure because this violates the bond angle, which is supposed to be 180. So I would like you to start with the triple bond. Now for 1-butyne, for example, you start with the triple bond and then you have to add 2 more carbons. So then you have to go straight line from here because that's 1, 2, 3 carbons, and then you can go ahead and give it an angle. So you can see it kind of looks weird, but that's how we write alkynes. Okay, so you have to be a little careful. Now for butyne, it's in the middle, right? The triple bond is in the middle. So for 2-butyne, you start like this, and then you will have the 2 lines. Now you have to be very good in your handwriting. Otherwise, sometimes if you just do this, then sometimes it's not clear whether you actually have a carbon here or not. Okay, so be clear in your drawing. What I will suggest that you do for yourself is, I don't know why I raised that, but do this. Okay, give yourself some space here, and that's how you will know that there is a bond. And I know I'm kind of contradicting the space and the bond, but it can help you, okay, a little bit. Or you can write the thing, write the structure out and the line structure, and then you can join it together. So that way, when you count, then you have 4, and you want to make sure you have enough carbons there, okay, because sometimes the length of the bond is not clear for me. So just make sure, that you have nice structures. Okay, so more on the nomenclature again. So now in these cases for alkynes take priority over substituents as we did for alkenes also. Okay, so if you have a substituent, don't worry about it. That's not going to get the priority. Alkyne is going to get the priority. So again, now this one is 6-chlorohept-2-ine. So again, remember to put the number just before the functional group. Okay, now if you have an alkene and an alkyne, then you just go alphabetical, which is then 5-ene and 1-ine. So which means that the ine is getting priority, and so therefore you start numbering also from the alkyne. Okay, all right, and why it got priority is because alphabetical also. Okay, all right, so generally you will find alkynes in straight chains. you don't usually find alkynes in ring structures, okay, because the 180-degree bond angle is really very hard to form for large rings, and so you need to have a really large ring in order to support that kind of a bond angle. So generally you won't find it in ring structures. But anyhow, so that's alkynes. And what else do I want to say here? Let me see. Yeah, just here, if you can see how the numbers are, just before the functional group. Okay, so you can see the value of having the numbering, the locant, just before the functional group. It helps. The physical properties of alkynes, they're very similar to alkenes and alkynes, so there's really not much more to say here. Small molecular weight alkynes are going to be gases, and then, as the molecular weight increases, they turn into liquids and solids. Solubility in water is not that much at all because everything is nonpolar. So because they're not soluble, we have to talk about density. They have lower density than water, and the odor is generally not that great. Now, we don't deal so much in the lab with alkynes. I don't think I have any lab with any alkynes in Palm Beach State, so, but anyway, you won't get to smell any of the alkynes. Okay, so regarding the applications for alkynes, the one that I mentioned just now was the acetylene torch used in welding because it burns with a very high temperature, so you need very high temperature for metals, so acetylene is very good for that. Usually, as I said, alkynes, we don't use much in the lab, so it's really just used industrially for making alkenes or alkanes or making functional groups for synthesis. Other than that, it's not that common. Now for synthesis for alkynes, so usually all the reactions are going to be elimination reaction, and most of them are going to be E2 mechanisms. Okay, now we have not made alkynes before. So alkyl halides we have, okay, so you have to think about how you have made alkyl halides. So the first synthesis we are covering is from alkyl halides. So remember, you made this one from an alkene, right? So, but anyhow, we'll get to that also. But anyway, you need to have two halides in order to do two eliminations, okay, to form the alkyne. So here, sodium amide is a really strong base, which is used then for making alkynes. You will see that a lot in alkyne synthesis. Okay, so what is being removed is going to be, of course, the hydrogen and the Br. So again, it's a 1-2 elimination, okay, but it's not, it's not a 1-1 elimination or 2-2 elimination. So the H and the Br, and then the H and the Br, right? So that's how things are getting eliminated to give the triple bond, okay, for the alkyne. Then alkynes are also internal and terminal, right? So here is an internal alkyne, which is like a 2-butyne, and then 1-butyne would be a terminal alkyne. Let me remove these because they look like alkenes. So how do you make internal versus terminal? So for terminal, if you were using this kind of an halide, dihalide, then to make an internal halide, internal alkyne, you would use sodium amide. This, by the way, this is excess, my short term for excess. And for making the terminal alkyne, you would use a bulky base, okay, because a bulky base, remember, it was more like a Hoffman product, a Hoffman kind of elimination, to form the more terminal kind of alkene, and in this case now an alkyne. Okay, so use small base. Now, can you use other bases in there? So we've used other bases like methoxide and hydroxide. I would say no, because you need a really strong base in order to do these eliminations. Okay, so I would just stick with sodium amide over here and be careful. All right, so don't use any other base unless you've checked the pKa and whatnot, okay, for all of these bases. So anyhow, I think that's about it. Now, why do we need the water here? Generally, water is added in order to do the workup. Now, in some cases, I've not been adding water, but water here is a good thing. So here also, if you add water, that's fine, because what happens is that you have to give this one a proton, okay, at the end. So in this one there is no proton, so it doesn't matter, but here you need a proton. So sometimes, when you do the workup, and that's why I didn't add the water here, when you do the workup, you're already adding the proton there. Okay, so that synthesis that we just did was with the dihalide, but what if you just had the one halide? Okay, so one halide is going to give you only one double bond, right? So you can't get two bonds from there, two unsaturations from there. So you have to do elimination first in order to get an alkene. Once you get an alkene, then you have to do bromination. Then once you have the two bromines on there, now you can go ahead and do the elimination. So the location of the double bond will give you an idea of where the triple bond is going to be. So for example, if I were to use, small base over here, like a methoxide, then maybe I get an internal alkene, and then I can do the same thing, where I can now do the bromination here. So once I get this, so now when I do the last part where sodium amide to do the elimination, so now I'm going to get an internal alkyne. Okay, so one carbon on one side and then two carbons on the other side. So it depends on what kind of base you use, especially like if you have a secondary halide like this one. Okay, so I went ahead and made a terminal alkyne, but you can see how you can actually make an internal alkyne also. So by now, I hope you're feeling more comfortable with synthesis, so you can manipulate a little bit and use all the knowledge that you have for elimination and addition reactions in order to get to a place where you are. If you just, not to sidetrack too much, but if you look at the synthesis, this is 1, 2, it's a 3-step synthesis. It's not too long, okay, but it's still 3 steps. So which means that you have to kind of think a little bit ahead as to what you're trying to make. So if I were to give you, that make this alkyne for me, you will have to see what kind of substrate you need, and I can say, okay, just make this from a alkyl halide or make it from a dihalide. So I can specify where I would like you to start. Okay, so that will then determine how long of a synthesis you're going to have. So then synthesis from alkenes, and as I just mentioned, you cannot make alkynes from alkenes. You just cannot do elimination from alkene to get a double bond. There's nothing you can do here. There's no elimination possible. Okay, so which means you have to add a group that is a leaving group, which is either bromine or chlorine. So once you've added those halogens on there, then you can go ahead and do elimination. So essentially, what have we done? We've come back to alkyl halides, right? That's what happened. So which means that your elimination right now is really essentially from alkyl halides. How you get to the alkyl halide is up to you, whether it's from alkenes, whether it's from, if you have a single halide, then you have to do elimination, get to an alkene. You can see, okay, it's not a one-step kind of a thing, unless you have a dihalide, then it's a one-step synthesis. You cannot really make alkynes from alcohol, so this is a little bit misleading kind of a title, but what you have to do is from an alcohol you still have to make an alkene. Okay, that's what you have to do. So if you think that, okay, I used a dihalide, I should be able to use a diol in order to dehydrate that to make an alkyne, that's not going to happen. Okay, so you cannot do that. So you start with an alcohol. If you are given an alcohol, again, you bring it to an alkene, and then of course the first step is to brominate to get the dihalide, and then the second step is going to be to do the elimination. Okay, and so you can see everything is leading to alkenes and then forming a dihalide, okay, in order to form an alkyne. So that's going to be your steps that you need. Okay, what are we doing here? Show how you'll carry out the synthesis of the alkynes below from starting materials given. So here is your synthesis, right? So this one is from an alcohol. This is from a secondary alcohol. This is from a primary alcohol. This one I'm getting an internal alkyne, and in this I'm getting a terminal alkyne. That's what I'm making. So let's look at how to go from here, from a secondary to an internal alkyne. I've given you all the explanation over here, when you're reading the PowerPoint, so you know what my thought process is. So my thought process is that I'm going to go ahead and dehydrate this alcohol. Now, since this is a secondary alcohol, I'm going to get an internal alkene. Okay, and why I will get that is because it's a carbocation mechanism, right? Dehydration of alcohol to give alkene is E1 mechanism, and I will get the Zaitse's product in that. So once I have the alkene, then not a problem. I add Cl2, get my dihalide, and then of course I just have to do elimination, right? 2 eliminations, and I get an internal alkyne. No problems, okay, for the first one. Now in the second one, everything is happening terminally, okay, so which means that I have to somehow get a terminal alkene, okay. So this alcohol, if I dehydrate that, I am not going to get a terminal alkene, because if it's an E1 mechanism, rearrangement is going to occur, and if it occurs, then I am going to get an internal alkene. Okay, so I cannot do this anymore, because this, as I said, will give me this 1 2 3 4 5 1 2 3 4 5, and then I will get this kind of an alkene. So I don't want to do that, okay, because once I get this kind of an alkene, then I'm going to have a very hard time getting to a terminal alkyne. So I want to get something on this carbon, okay, and that I can get with HCl. Now, what is HCl doing? This is hydrochloric acid. So now if I do substitution on this, so remember what I'm doing here is I'm making this a good leaving group. So by converting it into OH2 plus, when this leaves, what happens? A hydrogen is going to shift from there to there. And so then the Cl is going to attack on that carbon, right? That's how I'm getting this 2-chloro over here, all right? So I can't get the chlorine right where the OH is, not right now. Eventually I'll be able to, but not right now, okay? But I get my chlorine on the second carbon because of rearrangement. Now, once I have this chlorine, now I know how to get a terminal alkene from there, which is a Hofmann alkene, by using a bulky base. Okay, so that I know how to do, and I've done that now. So once I have the alkene, now I just have to do the chlorination, and then I have to do the elimination. Okay, so because the 2 chlorines are 1 and 2, there is no other place to form the alkyne than a terminal. So I hope you understand how this is all working. You really have to have a thought process into how you want your functional groups to be where you want them to be. Okay, so a lot of times you cannot just think of these things in your head. You have to write it out. Okay, and I've always encouraged you to do that, is that, whenever you're thinking about something, when you're in doubt, just write it out, write the synthesis, see if it's making any sense to you, But the thing about synthesis, okay, I'll tell you, is that you have to know all the reaction mechanisms that we've been talking about. So, when I was talking about these syntheses, I was mentioning, E1, E2, SN1, SN2. So you have to know your mechanisms, and you have to know your reagents also, okay, like Cl2 and then amide. So you have to know your reagents as well to be comfortable to do all these syntheses. Okay, that's it in this one.